Let's talk about some common analytics techniques that analysts use. The first thing you do in a project often is to determine what the right tables to use are. Might be that you've worked with them in the past, or you have to ask someone else about what tables, where certain data lives. And it's important to then understand what that table represents and validate that, especially answering the question, what does one row represent in this table? It's important to avoid duplicate issues. Then you might need to manipulate that data in the table that you're in. Determine which columns to select. Maybe you need to create some columns. What rows need to be filtered and what tables need to be brought together in order to get the ultimate table that you'll use for your analysis. Interactive dashboarding is another popular technique that we've talked about as we went through Power BI and Tableau as a couple of dashboarding examples, but that involves importing data into an interactive visualization platform, creating interactive filters, cards, tables, and charts, designing your dashboard, and ultimately publishing it. Another data manipulation technique is aggregating or grouping. SQL does this really well. This involves rolling up totals to compare across the different values of a column, aggregating data together. Trending is a very important thing to do. You don't want to just look at a comparison over an entire time period and not consider how that might be changing over time. So monitoring a certain metric by week, by month, by quarter, by year, and how that is potentially changing over time is extremely important. Performing statistical analysis is a critical skill that especially a data scientist is expected to be able to do. You might conduct a t-test to assess whether there's a statistical significance across two groups. It's one thing to just look at how different two groups are. It's another thing to determine whether that's potentially just due to random chance or actually statistically significant. When it comes to data science models, data scientists need to have that skill. They need to be able to build models that either predict something into the future, maybe which customer is going to buy or which customer has a higher likelihood of buying, or what sales will be for the next 5 months, or prescribe an impact. What is the impact of this variable on this other variable? Data science modeling is a great technique for accomplishing that. And then there's A/B testing. This is the best way to determine the value that a certain treatment or initiative is driving. It involves randomly assigning observations, which could be people or products or geographies, but randomly selecting observations to belong to a test group, which will receive a certain treatment or initiative, and a control group, which will not. And by randomly assigning observations to each group, the only thing that is different across the groups in aggregate is the fact that the test group received a treatment, which means that any differences across the test and control group in the metric you're trying to measure can be ascribed to the treatment itself. And then you can use a statistical analysis like a t-test to determine whether that difference is statistically significant. That's an example of how these different techniques, and this is certainly not all of the techniques an analyst would use, but these are several techniques that can be used in isolation or together to ultimately accomplish an analysis objective. Let's dive into each one of these. Exploring data. Exploring data involves finding and understanding a specific data table. And a data table is simply made up of a set of rows and a set of columns. We have an example over here. This would be a table that is one row per month product combination with the number of sales that occurred for that particular month product combination. It's a set of rows and a set of columns. Simple as that. Now, when you begin an analysis, especially if you're at a new company or you're working on an area that you haven't done much analysis in the past, you may need to go to another analyst or the business intelligence or IT team to ask for access to a table to find out what the table is called, where the information that you're looking for resides, and you may even be able to get a starting SQL query from them, which might have some common filters that should be considered. Perhaps the most popular columns or the key columns that you might want to start selecting. It can give you a great hint of where to start if you can get a SQL query, and of course ask some clarification questions. Now, it is absolutely critical that you understand for every data table you're using this key question, and that is, what does one row represent in this table? In our table on the right here, you can see that there is one row for every month product combination. Other tables might be one row per product, one row per month, one row per sale, one row per customer, but you need to, one, answer that question, and two, validate that that's the case. And we'll eventually, when we get into SQL, talk about how you can validate what one row represents in that table. But if you can't answer that question, or maybe you have an idea of what one row represents, but that's not actually what one row represents, you can easily run into duplicate issues, and that's where attention to detail can fall apart. Let's talk about data manipulation, and especially data manipulation in SQL, which I highly recommend learning. And we'll have a dedicated session to that. Let's just go over some of the basics of SQL for now. First, there's a select statement. This identifies which columns to include in the resulting data table. We're ultimately writing a SQL query that will run. We saw an example of that in SQL Server Management Studio in the brief SQL section we covered. It starts with a select statement that covers what you want to pull, and in some cases you can even define a new calculation. This is an example where we're taking the sales variable and the existing price variable, multiplying them together to create a new revenue variable. That'll be an extra column in our data set. We use variable and column interchangeably. We need to specify in a SQL query which table the information will come from. In this case, we're starting with one called sales table. And then in the next line, we're actually joining that with another table, and we specify how to join those tables. We want to join the rows in the first table with the rows in the second table where the value within each table's product column matches. This isn't optional, but in a lot of cases, you'll want to have a where statement that filters the results to a certain requirement. In this case, we're only going to return rows where the product column from the sales table equals apples. We're not going to include those orange rows. And then oftentimes in a SQL query, not always, you'll have an order by statement that tells you how to order the data. Now there are other SQL clauses as well, optional, but this SQL query would run and it would return a data set that has, for all the rows where product equals apples, the month, the price, the sales, and the revenue column. Again, it's absolutely critical to answer the question for the tables you're pulling from and the table that you're about to create with the SQL query, what does one row represent? And validate that that's the case. Okay, same data set, but now we've brought it into an interactive dashboard. In particular, we have created a title, we have some slicers on the side that we can essentially use to click and filter down to just apples or just oranges or all of the above. If we select all, we can filter on certain months using this month filter we've created. And we've created a table here that has 3 columns. We could create charts in addition. You can see I've used some conditional formatting bars in the background of sales here. Just a way to visualize how sales have been changing by month, by product. There are lots of other ways we could visualize as well. And the idea is that if we use these slicers, it'll filter down this table and any other visualizations that we'd created as well. So we create this after importing the data, perhaps using a SQL query in a platform like Power BI. And after we've created it, we would publish it and make it available via a link to our stakeholders. And now they can interact with it and see the latest data whenever they need to. No manual work involved. Now let's talk about aggregating and grouping, and I don't think there's a better tool to do that than SQL. Here's an example of a SQL query that aggregates sales by product. you can see we're using an aggregation function in SQL. This is sum. You can also use things like count and min and average, but we are summing sales and we're summing them by product. And this is key, we are grouping by product. That allows us to have the following output. This is what we might see in either Power BI or perhaps SQL Server Management Studio, whatever engine we're running our SQL query in. Now we just get 2 rows, 1 per product, and what it's done is it's compressed all the rows for apples, all the rows for oranges, all the rows for each value within the column that you are grouping by. It's all boiled down to 1 row now that in this case is the sum of sales. And it shows us at a high level what the sum of apples and oranges are over this time period. Really neat. Now, before we saw that there were more apple sales than orange sales over our entire time period, January 2022 to the beginning of 2023. But it's also a good idea to check if that difference has always been the case, and that's where trending comes into play. On the right side, we have created a trending chart in Power BI. This could also be created in Excel or even in a SQL query where you're grouping by month perhaps. We can see in this case it's important to look at the difference over time, because even though apples overall during this time period had more sales than oranges, in the last couple of months, and even more so in the latest month, orange sales have been significantly higher than apples. You would miss that if you just looked at the overall comparison by product and you didn't trend it over time. You can also sometimes identify data issues this way. Now, it's also very common to look at the year-over-year change over time, and that's important because in some cases a trend could be driven by seasonality. So for instance, this spike we see here, we saw the same spike last year. Most metrics, sales or whatnot, have at least some amount of seasonality, and that's where year over year comes in, and looking at not just what's the year over year for this time period, but how has that year over year difference been trending. Now, it's very important to understand and look back and see, well, what's really driving that? Was this driven by, if the year-over-year trend is changing, is this driven by a abnormally low last year and that's why it's high this year? Or is it an abnormal high this year and that's what's driving an increase in year-over-year growth? So keep that in mind when you're looking at year-over-year growth, but it is very common to look at year-over-year change over time, by month, by quarter, by week. All right, now we're getting into data science. Let's talk about statistical analysis. At the heart of most statistical analysis techniques is the assumption of a distribution. In fact, there's a term for models that use that. The term parametric means it's based on an assumption of a distribution. A lot of these techniques used a normal distribution or a bell curve. It's a very commonly seen distribution. Some examples of statistical tests include hypothesis testing, such as a t-test, or building a confidence interval for a metric, or even getting into certain types of regression. Now, in practice, I would say most analysts, especially outside of regulated industries like the medical industry, rarely take the time to actually apply a statistical test. Instead, it's often substituted for a general check to make sure that the difference is substantial. So one group, it's not saying, well, this group has a value of 100 versus 101. That's not a very big difference from a percentage perspective. And that each one of those averages or sums, that it's based on a sufficient sample. Maybe making sure that each group is based on at least 100 observations. So really simple checks on statistical significance, but not necessarily taking the time to actually compute a t-test. That's just not saying that's the right or wrong thing, but that's often the way it goes applying analytics at a lot of companies, especially your analytics level 1 and level 2 maturity companies. Now on the right side, I did want to show an example of a distribution and an example of a t-test or confidence interval. So we have our mean, our true mean here, And let's say that we pulled a certain sample and we found that the mean of that sample, the average of that sample, was up here, was 3 standard deviations higher than the true mean. Or a hypothesized mean. Our analysis would look at the likelihood that if we actually observed this kind of mean for a certain sample size that we have observed it among, what is the likelihood that the true mean actually is our hypothesized mean? And if it's a very low likelihood that we could see an average on a certain sample size that high, with the true mean being this level, if there's only a 2 or 1% likelihood of that being the case, we would often reject the null hypothesis and state that we are quite confident that the mean of the population is higher than the original hypothesized mean. Just one example of a statistical test. Now let's talk about data science modeling, which is sometimes referred to as machine learning or artificial intelligence. There's a fine line between all of those terms, and a lot of people think about them differently. So we'll combine them together for now at least. Now within data science modeling, there are predictive models and there are prescriptive models. Predictive models focus on making some kind of a prediction for the purpose of perhaps planning. How many sales do we think we're going to have next month so that we can plan our staff that's going to need to manufacture a certain amount of product? Or for prioritization, which consumers or which prospects do we think are most likely to buy so that we can make sure to call them first, for instance. And then when it comes to prescriptive models, we're trying to understand what is the causal relationship. Is there a causal relationship between variables? We might want to do this to calculate the return on investment. We need to know exactly how many sales a certain initiative is driving. Or perhaps we want to build a prescriptive model to identify ways to drive more or less of a particular variable, a particular thing we want to measure and understand. Now, sometimes organizations will employ a data engineer that we've talked about in order to build the data set, and then a data scientist to actually build the model. Now, in other organizations, it's kind of a all hands on deck approach where an analyst might be the one to create a visualization, perform an ad hoc analysis, build a model, build the data set for the model, all of the above. Every organization is different. There's different levels of specialization. Well, and there's also a lot of different types of data science models, and we have a few examples of those on the right here. So first we have a regression model. This is an example of a parametric model. A regression model relies on a certain distribution. If it's a linear model, it relies on the normal distribution. Then there's non-parametric models that don't rely on a variable having a particular distribution. A decision tree is an example of that. A random forest model is a more advanced version of a decision tree. It's a set of many trees built in a way to optimize what's called the bias variance trade-off. We'll talk more about that when we get into data science. And then there's neural network models or deep learning models, and those are some of the most advanced data science models that exist, used to do things like determine what's in an image or what sound something made, all kinds of things. And that's a quick overview of data science modeling. Again, we'll have a dedicated session to this later on in the series. A/B testing, one of my favorite topics because it is absolutely the best way to determine if an initiative is working. It's also known as a scientific experiment. That's essentially what we do when we take a group of observations, which could be people or products or geographies, as we said before, and randomly assign about half of them to a test or treatment group and half of them to a control group. Now, it doesn't have to be half. In fact, if you're really not sure this is going to work, you might go with a 20% or 10% group, especially if you have a large number of observations. That should be fine. Or in some cases, people are very confident. Want to have a holdout population to know the impact of the change, and they might go with 80-90% in the treatment group and 10 or 20% in the holdout group. But you'll get the absolute best read on the test if you take 50% of the population and assign it randomly to the treatment group or the test group, and the remainder to the control group. The great thing about this approach is that the only thing that is different, if they are truly randomly assigned to the test and control groups, is that the treatment will be applied to the test group, which means that when you observe the differences across the two groups, any differences, especially if they're statistically significant, can be applied to the treatment. It is a very robust approach. There's no selection bias through the random selection process. Now, what you might do, especially as you even as you start to design the A/B test, maybe you've randomly selected the test and control group, and you just want to be sure that it was absolutely random. You can use Excel random generation or Python random generation, but you want to be sure that these two groups are truly random. What you might do is select the groups and then plot out their performance in the metric that you want to measure, like sales, for instance. Monitor what the difference has been over time. And what you should see is that the two groups are essentially lockstep over time. So again, we're doing a trending analysis here, and you will see some natural variation, some randomness in there. So in this case, in this particular month, the control group performed a little bit better than the test group. And that was the case for the next month too. And then the test group performed a little bit better. But what you should see is that there's not a consistent difference across the two groups, especially prior to introducing the treatment. So in this case, there's a month when the treatment gets applied, maybe it's July 2022 in this case, and that's where we're really interested in what happens next between these two groups. What happens to the test group? In some cases that we want the metric to go up, in some cases the goal could be to bring a metric down. Whatever it is, what we should see is that there starts to be some separation across the groups if the treatment is actually having some kind of an impact. And so in this case, we see that the two groups are pretty much in lockstep. A treatment gets applied, and then, especially after 2 to 3 months, we start to see a consistent difference between the two. Now, we would want to go and do a t-test to make sure that difference is statistically significant, but at least visually you can see there is a consistent difference where the test group is consistently performing higher than the control group, whereas before we introduced that treatment, they were pretty much performing at the same level. So just visually looking at this, I would be pretty confident about saying that the treatment had at least some impact on average sales per customer. This is a great visual to show to an executive to prove that this treatment had an impact. Now, at the end of the A/B test, we'll want to assess the difference between the test and control groups before the test, pre-test, and post-test. We might create a visual like this that highlights the overall differences during those two time periods. In this case, since the test started, the treatment was introduced to the test group in July 2022. Our pre-test period, January 2022 through June 2022, we saw a very minor difference across the groups. They were randomly selected, and so there shouldn't be a very large difference. There'll always be somewhat of a difference due to random variation, but in this case we could see that the test group, their average sales per customer was 98.5 versus the control groups was 100.3. So the test group was 1.8% lower in terms of average sales per customer than the control group in the pre-test period. We want to compare that to what the difference was like in the post-test period, in this case July 2022 through February 2023. And during that time period, we actually saw that the test group was 21.6% higher in terms of average sales per customer than the control group. So what we might do is, if we thought that there was a possibility, there was a systemic difference, we might control for the pre-test difference of negative 1.8%, subtract that out from the difference we saw in the post-test period, and what we would suggest is that the treatment introduced in July 2022 to the test group had the impact of increasing sales per customer by 23 0.4%. We can also see this visually. We saw the over time visual, but sometimes it's nice to see things aggregated up by time period, by test group or control group. We see again during the pre-period, the groups are very similar in terms of average sales per customer, and post-period, the groups are quite different. The test group is clearly higher than the control group. So that's another way of visually showing what the impact was. Now another thing, and before we move on, we would want to conduct perhaps a t-test, a statistical test, to determine whether that difference was statistically significant. Now you might also decide to build a data science model that could, one, be used to determine whether there's a statistical significance. So you could do a t-test, but you could also set it up as a regression model. And your target variable would be whether or not a customer was in the test group. And you'd be seeing what impact that had on sales per customer. That's another way of measuring the statistical significance. If the p-value of that is the observation in the test group or not, if the p-value of that coefficient is positive and is statistically significant, yes, we did. We had an impact and it's statistically significant. Now, another thing you can do, especially if you get into a response model, a mixed model that has interaction variables, is you might be able to assess whether, not just whether there's an overall positive impact or negative impact of a treatment, but whether that treatment impact varies depending on other characteristics. Maybe the treatment works really well in a certain characteristic or a certain profile of customer, and not so much in other profiles. You can use interaction variables to assess whether that's the case.